This podcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. We'll try to answer as many questions as we can. You can enlarge the slide window by clicking on the screen icon in the lower right-hand corner of the slide window. If you have any technical problems viewing or hearing this presentation, please click on the support button at the top right of the presentation window, or submit your problem through the green Q&A button lower left. This is an educational webinar and thus offers free continuing education credits. After the webinar is over, please click on the CE button located in the bottom left-hand corner of your webpage and follow the process of obtaining your credits. I would now like to introduce today's speaker, Dr. Randall Wolcott. Dr. Wolcott is the founder of the Southwest Regional Wound Care Center in Lubbock, Texas. The Wound Care Center specializes in biofilm-based wound care. The Wound Care Center offers state-of-the-art technology with molecular diagnostics and state-of-the-art alternative medicine, including customized topical wound gels. He is passionate about healing wounds. I will now turn it over to Dr. Wolcott for his presentation.
Hello, I'm Dr. Ray Wolcott, and we want to welcome you to this Lab-Roots presentation. The title is a little bit intimidating, and basically what we're going to talk about is how molecular methods, not just DNA methods, have expanded a little bit, how the identification of microorganisms is becoming more sophisticated, and then we'll broaden it out. The last time I spoke, it was about chronic wounds. This time we're going to broaden it out to chronic infections, and I think it will include more of your interests if we do that. Erasmus a long time ago said, in the land of the blind, the one-eyed man is king. And basically, when you have a diagnostic test, when you can look in and see the reality of what's happening in whatever you're interested in, you have vision. But I would caution Erasmus, and I would say, it's not just what you see, it's what you understand. And what I hope I can do for you is get you excited about this stuff, where it's going. This truly is a quantum shift in medicine. And the diagnostic tests, the ability to see the microorganisms in reality and with measurements with scientific certainty is changing the whole game. But before I go into that, let me talk to you about my conflict of interest. I am a part owner in a laboratory, a molecular laboratory, and so I want to brag about it a little bit. NASA came to our laboratory and said, hey, we got this Mars rover, the Curiosity, and we want to make sure there's no microbes on that. And so we did our DNA-based evaluation, and there was no microbes on that. And that was cool, and that gives you a lot of credibility because you work with NASA, that's really cool. But then we got to thinking, why did they care? I mean, what's the matter if we send some bacteria up to Mars? Well, what we found was that the Martians, ever since the War of the Worlds movie, they don't like our bacteria. And the point on this is what Mark Twain said so long ago. He said back in the 1800s, there's lies, there's damn lies, and then there's statistics. And the more papers I read, I realize that people can put their statistics through just about any point. I'm going to try to be as open and honest on this as we can. I know I've got a position in this, I've got a bias. But, hopefully we can tell you what's set in science, what's certain, and what we think, and where we think this is going. So it's from a clinical perspective more than a scientific perspective. So let's start with chronic infections. You know that even non-health care professionals know that what a chronic infection is versus an acute infection. And basically, acute infection, comes quickly. You get 3 to 5 to 7 days of antibiotics, it clears the infection, and it doesn't come back. Chronic infections, well, they wax and inflame, you use antibiotics, you get a little bit better. And they come back, they're chronic. And so, but if you ask physicians, what is a chronic infection? They'll sort of refer to the infections of the bacteria, but the host must be broken. There must be poor perfusion, or there must be scar tissue, or the immune system is impaired, or something like that. That's the way they think of chronic infections, but that's just not true. Okay, it is a microbial-based problem, and that's what we're going to try to discuss with this slide. Is just what is a chronic infection, and we're going to the scope of the problem. So, way back in Dark Ages, 7 years ago, we were trying to give information to clinicians. When should they think that they're dealing with a biofilm-based infection? And what we found was everything that we found to link to biofilm infection was really a description of a chronic infection. And then last year, the European Infectious Disease Society came out with some guidelines on chronic infections. And what they started, their guideline, their abstract on their list was biofilms cause chronic infections. So that's a settled science, okay? So this is the best of the best across the continent of Europe, and it's supported by many microbiologists and scientists throughout the United States. And basically, it's this bacteria growing as biofilms that causes the symptom complex that we call a chronic infection, whether it's in the sinus, whether it's in the gut, whether it's on the heart valve, whether it's in the lung, or for us, it's on the skin of chronic wound. So this is a really important, again, quantum shift in medicine, because now we know what our target is. We have a clear understanding of what is a chronic infection. So what does that mean? Well, in the scope of medicine, every tissue can suffer a chronic infection. Whether it's a sinus, whether it's, let's see if I can give you some guidance here, whether it's a sinus or whether it's cystic fibrosis or COPD, whether it's an infected medical device like a hip or a knee, an infected heart valve or for us, skin, a chronic wound or a burn. That's biofilm. And if you look at how each discipline has come to treat their biofilm disease, it's usually with episodic antibiotics, neglect, let the patient go, and then when the tissue that's getting infected, like the sinus and the lungs, if it's disintegrated, then they strip the sinuses, they transplant the lungs with cystic fibrosis, they replace the heart valve, they take out the prosthesis for healthcare providers who cut off the leg. Now, my point is these are infections. These are chronic infections. We know the target. And so the better way to treat that infection is not to remove body parts, but for us to understand that, and that's where diagnostic test comes in, cure that, which is the holy grail, and prevent those loss of limb, loss of heart valve, just stop the carnage of removing body parts. To make it more personal, we've launched into a different area of research, and that's atherosclerosis. And what we found, and there's a couple articles just in case you're interested in that, is kind of the mechanism of how biofilm could cause atherosclerosis. And then the second thing is we were able to go into atherosclerotic plaques, the hardest to get in situ, and find the biofilm structures of clusters and voids in between. So that arrangement of bacteria cannot be contamination. So it's grown there. It's grown in these very dense clusters, which we call biofilm. So there is biofilm atherosclerosis. So now that makes it personal. There's not a one of us out there that doesn't have that. There's not a one of you listeners and myself that doesn't have periodontal disease. And then a third of us have other chronic infections. So this is a very, very wide problem throughout medicine. And that's why the diagnostic test is so important. Well, I'm a wound care physician. Wounds are accessible. Atherosclerotic plaques are hard. Heart valves are hard. Sinuses are hard to get to. But wounds are chronic infections of skin structures. And we can use that to find out the basic principles of the host microbe interaction in this kind of infection. And then take those principles that we learned in wounds and apply them across the other types of chronic infections. Chronic wounds are chronic infections. That is not science. That's the shift that's taking place in the wound care community. So this is a patient that was sent to me from New Mexico, and the provider called me up and said, I have this patient with pyoderma gangrenosum, and this patient has a chronic granulation tissue. And we watched this wound for 3 or 4 months, and it's just eaten into her leg, and we need something done. But we know we can't treat it because you don't treat pyoderma. So for you that don't know about pyoderma gangrenosum, if you read it, it causes a pathogenic response, a hyperinflammatory response that causes tissue damage that makes it get worse. So, I mean, the provider was correct in that, but this is not granulation tissue, this is dead tissue. Now, the reason I use this patient as an illustration is we always talk about the host being the root or the cause of the chronic wound, diabetes, poor circulation, dependent pressure, neuropathy, an impaired immune system, and the list goes on. There's always they're thinking about the host as the reason why this lady doesn't have it. She has no autoimmune diseases or whatever. What she has is bacteria eating down into her flesh. So we did do debridement, but we did debridement by and control the microbes because we had a diagnostic test. And then within about 3.5 months, you see the pictures to the right, we had granulation tissue, and that's granular. You see the little lumps, grains, and you see the red color and stuff. So there is no such thing as necrotic granulation tissue. But at the end of the day, it's not host impairments that causes wound. It's a chronic infection that causes the wound. So how do we prove that? So let's start at the beginning. You have a defect through the skin. You've got this deep cavity down in the subcutaneous tissue, tendon, the muscle, and stuff like that. And there's no question that there's some bacteria in that. Okay, so bacteria can do one of 3 things. It can do something positive, like a commensal. It can help that wound heal. Well, commensals have communication with the host. They have specific cells that communicate with them, specific cytokines, and those mechanisms are more robust than we're able to imagine. Well, the muscle, tendon, bone, subcutaneous tissue doesn't contain those cells. It doesn't contain those cytokines. So there can never be commensals in one effect. It's a permissive environment. And we want to push back when we say, well, this is caused by staph epidermidis. This one, that's what's infected. This is what's commensal. It cannot cause infection. That's not true. It's not infected when it's under host control. But when it gets in that permissive environment, surely it can cause infection. The other thing the bacteria can do is just be a contaminant. And like this picture here, this is some extracellular matrix of the host, and there's a single bacteria there. And that's what you expect. You expect a few single cell or clusters of bacteria that spread around on the wound bed, and they're not doing any harm, and we know what a contaminant is. But then what do you do about this? In this one, we have rods. We have some very small cocci down here. We have some bigger cocci in other places. So this is a polymicrobial group of bacteria. You see these strands of material that are binding into the host surface. Well, that's host protein. That's fibrinogen that's been polymerized by and it weaves itself in. It also puts a coat of sugars around itself. So there's a matrix. So that is a biofilm. It's polymicrobial. It's a encased in matrix material, and it's attached to a surface. Okay, so this is a way that bacteria grows that's fundamentally different than individual cytonic bacteria. Again, the individual cytonic bacteria invade tissue, digest tissue, and have a slash or predatory type of strategies across infection. And so you see things like cellulitis or strep throat or sepsis. And single course antibiotics takes care of that because they're not protected. What we're talking about in biofilm is this community of bacteria that's encased in a cell-secreted matrix that's bound down to the surface with host proteins that expresses a vastly different part of its genome. So it's more like a caterpillar versus a butterfly for the mycotic bacteria. So these are radically different than the bacteria that you learned about the microbiology causing infection. But the strategy is quite different also. It has to stay secure to the surface. If it eats the surface, it will be released to the environment and it will fail. But if it inflames the surface, it can have plasma exudate that comes out and that's what feeds the biofilm. So it's a different infection strategy. And the question is can this bacteria cause what we see in Lyme? Can it cause the wound to dilate? Can it cause the wound to form that sloppy exudate? Can we see all the chronic wound behaviors directly explained by this material that's on the surface of the wound? Well, the answer is yes. And these are slides from Northwestern, Dr. Musco, Dr. Galliano. I got to present right after Dr. Galliano, and I could kind of get those slides because he was using a term called biofilm way back in 2008. And basically, what he was showing was in their rabbit ear model, they could debride these little punched out wounds and impair the circulation to the ear. And then 24 hours later, slough would reform. And they didn't call it slough. What they called it was biofilm. So what they did was they looked at this microscopically, they touched out those little holes, and they followed those. And on day 3, what they found was that this granulation gap, the base of the wound that they had touched out before, was significantly bigger for the biofilm than for the control. How significantly? It was 0.0001. So there's no question that the presence of the slough, the presence of the biofilm, delayed the healing of the mouse wound. So that's an important point to take forward. So remembering this work and looking forward, and then looking backwards at Koch's work way back in the 1800s, 1860s, what we wanted to do was use a rational way to say, does the microbiota on the surface of the wound, the polymicrobial biofilm that we find on human wounds, is that the cause of the human wound, or is it the host factors that cause that? And so I think this is a definitive study for that. So basically in Koch's model, you identify microorganism in the disease person, you identify, you purify it through culture, you put it into the animal model causing the same disease, and then you recover the bacteria. So that's what we did when they said pure culture. We took the biofilm intact and seeded it into the mouse wound. And so on day 0, that was a homogenized amount of slough that was harvested from a human patient, from a human wound. And then on day 4, you could see that in the mice that were seeded, that there was significant slough that would develop. There was significant exudate. There was significant delay in healing. And so we know we created the same disease in the mouse model. Then on a few days later, we harvested the bacteria. We correlated it back to the bacteria that was originally taken off the host and found that we had the same group of organisms that we started with in the human wound. There was a very high correlation. Whereas in controls, the wound healed normally. There was no significant slough, no significant exudate, and no delay over what you would expect from people who have a mouse. So, I mean, that's good science. That shows that the microbiota that's on the surface of a chronic wound, the microbiota that's involved in any chronic infection, is the cause of that infection. And we can have a host factor matter. We can augment host defenses, and we can help the host. But at the end of the day, it's the microbiota that's the main problem in these chronic infections. So I use this slide to talk about wound care, but it applies to all chronic infections, and that's the sad truth. The chronic infections aren't adequately diagnosed. 99.9% of chronic infections that are currently present in U.S. citizens today are not diagnosed. Because if you get a diagnostic test, it does not help in the treatment of that disease. So in wound care, we take very few cultures. In sinus, very few cultures. They do relatively outwards. I mean, it's not like we're treating an infectious disease. We might check the exacerbations or something, but it's not the routine diagnostic test in this chronic infection. And so for every mistake for not knowing, kind of for not looking, we don't look. And it's because our diagnostic test, the clinical culture that most physicians use, don't lead to better outcomes. We get the test, we get a report, it usually tells us 1 or 2 things, we treat those 1 or 2 things, and the wound doesn't get better, the sinus doesn't get better, the heart valve doesn't get better, it fails, and it's because of the limitation of the diagnostic test. A little over 2 years ago, I put that throw journal, don't even know the name of it. I got this picture of it. But what the author said kind of just rang, it got me passionate about this. What he said was, what if we could culture all bacteria? Well, basically, that's admitting that you can't culture all bacteria. At least one of us know that. We know the limitations of bacteria grow very slowly. So many different nutrients. Anaerobic bacteria need a different environment. It's difficult to grow bacteria. I've heard estimates like 99% of bacteria can't be cultured. I've heard estimates that 85% can't be cultured, but there's a large group of bacteria that can. I want you to look at that picture because that is what Koch was fighting way back when he started. What he found when he moved things on potatoes and other media, he found that he obtained polymicrobial communities. And he made the decision then that no, it's just a single organism, and I need a pure culture of that single thing that's causing the disease. Okay, and we're locked into that today. And that was a bias that was put into microbiology and clinical medicine over 100 years ago. So we want to change that because biofilm inherently is polymicrobial. It's multiple different species that reside in a single community, much like these different communities you see on the plate. So by its very origins, the petri dish, the agar, the nutrients that were used, put a bias into finding a single organism, and the nutrients that we put in, and the bias is we want to find gram-positive aerobic bacteria. So guess what we find with our culture? We find that, and we can see that in this diagram here. This data is getting a little bit over since 2003, but this is a culture show. And what you're seeing is, if you break into that 30%, what this is showing is about 60 to 65% of the bacteria that were identified in 1,400 samples were gram-positive aerobic bacteria. There's no anaerobes in there. Pseudomonas is underrepresented. There's very few gram-negatives. So, that's the bias of the culture. That is not the reality of the microbes on the world. That's what we get at. So we realized that, and so we went out in the literature and said, how can we identify what microorganisms are present in the world? And we can do it with great sensitivity and great specificity. And that's when the Human Microbiome Project data came out. Now, here are those specific two I was talking about. You can prove anything with those, but the bottom line, what the Human Microbiome Project came up with was CNS can help us identify what bacteria is there, and it can give us a relative quantification of which one's there. Now, the whole genomic surveys probably show a little bit better in this data down here, but that's a lot more expensive to do than the 16S. So, but now that data is coming along, and now with newer methodologies, the mass spec proteomics, the different and deeper methods for sequencing, the whole more data is coming online to not only identify microorganisms, but identify mobile genetic resistance factors, and also to help us with quantitative information. So it's becoming evolving, it's getting cheaper, and it's giving us more information as we go along. I won't call myself out as an expert in molecular methods. I'm the guy that uses it. I'm trying to give context for how important this is and how revolutionary, how this can move the ball in managing chronic infections. One of the old technologies, and this must be 30 years old, is 35, is real-time PCR. And the thing about real-time PCR is if you go to the infection point and you can find the CT number and you run some normative data on your plate, you can work backwards based on the anomalous material extracted to a ballpark figure of how many individual microbial cells are present in that sample. So you basically can say, you can get one of those exponential numbers of position flow so much. So you would say 10 to the fifth or 10 to the fourth fifth of such and such. So it gives you an idea of how much bacteria you have in your sample. It varies with the sampling methods. It varies with, there's a heterogeneity in chronic infection on where the bacteria is present. But in the end, it gives you a pretty good measure of how much bacteria you're dealing with. And we call that bacterial load. If that goes significantly up or it goes significantly down, you kind of have a feel for how effective your treatment is. So we like real-time PCR, mainly for the universal 16S, but also can tell us what bacteria is there. And if I know the MRSA is present, if I know the Pseudomonas is present, if I know that vancomycin resistance is present, I can alter my empiric therapy on day one instead of a week later or 2 weeks later. So PCR has the advantage of quick, rapid turnaround, and it can tell us about specific targets, and it has the absolute quantitative ability to tell us how much is there. Whereas sequencing is more relative. The quantification there is it says, well, it's 30% this, 20% that, but you don't know what the total is. But still, it tells you what your dominant bug is. So we looked at 3,000 different ways using data. And what we found was SNP is indeed present, and it's pretty exhaustive. But by Number 4, we have anaerobe, and down here we have Propionibacterium and Eosinophilus. So anaerobic species are breaking into our top 10, and yet we've never been able to culture with clinical cultures these bacteria, and we've never really been able to manage them. We can't see if we've impacted them in any way. Now we have a diagnostic test that does that. Okay? So, and then the other thing is these are polymicrobial. But if we usually treat at a genus level, and so what we did was we resolved all these different species for Staphylococcus into a single group, and what we found was that over 63% of the time there is a staph species.